All right, buddies. What? Class is recording today, yes. Good morning, ladies and gentlemen. Class recording has started. There we go. So, I should hold this up and get my webcam out so we can actually go. But hey, you know what? If you're not here, you miss the experience. So, all right. On Monday, we were talking about problem number 1 from this sheet where tension is acting as a centripetal force. So real quick, right, just to review, centripetal force, any force that's acting perpendicular to the current path that an object is traveling. That perpendicular force will change the direction of the motion, but not necessarily its speed. It won't make it go faster or slower, just change its direction. Any force can be a centripetal force as long as it's acting perpendicular to the current path of its motion. And so on Monday, we started talking about a situation where we might have a combination of forces that help or together create the centripetal force. And so we talked about this object swinging around in a vertical circle where we have, just like my ball on the string, where we swing it around, and instead of the circle being horizontal or parallel to the ground, now it's vertical or perpendicular to the ground. And so now we have to contend with gravity. That when we were doing, like, say, this problem, right? Yes, gravity was acting on that car as it was going around the corner, but it was balanced out by the normal force, and we didn't have to worry about it in terms of centripetal force. But when we have this object that is moving up and down and up and down and up and down, sometimes gravity, well, gravity's always pulling on it in the downward direction. Sometimes that's towards the middle of the circle, other times it's not. And so the first problem we did, number 1, part A, we talked about the object at the very top of the motion, and so we said there were 2 forces acting on that ball up at the top of the motion. Gravity, the weight force, it's always acting. It's always acting. We can't get rid of that, so it goes downward. And in this case, when the ball is at the top of the motion, that's pointing towards the middle. And so in this case, gravity is acting as a centripetal force. But we know from earlier that centripetal force has to have a magnitude equal to mv squared over r. The net force has to be equal to the centripetal force. So in this case here, we know that the string is also pulling. Tension always points towards the middle. So in this case, we have 2 forces that are pointing towards the middle. Together, they have to equal the centripetal force. We know the weight force, even though that's a lame W. We know the weight force because it's always just m times g. We can then rearrange that equation to figure out what the tension force is. Good there? Okay. Part B, we started now talking about the bottom of the motion. So now this ball has come down full circle. Here's the string, right? The string is still attached at that point right there, being held onto by my hand, and now the ball is all the way down at the bottom, okay? This still has to be true, that the net force acting on the ball has to be equal to the centripetal force. Regardless of where it comes from, we know that centripetal force has a magnitude equal to what? It's kind of weird to ask questions when only like 5 of you in class. So we know that this has to be mv squared over r. That the right-hand side of that equation has to be mv squared over r. Now it's just a matter of, okay, what does the left-hand side have to be? Well, it's net force, so let's draw ourselves a free body diagram. Regardless of the fact that now the ball is at the bottom of the motion, whereas previously it was up at the top of the motion, gravity is still acting on it. Gravity always acts downward, regardless of where the ball or where the string is. And gravity always has a magnitude equal to m times g. we figured out this number in the previous problem, right? 2.43, is that what it is? 2.94? 2.943. All right, so this is 2.943. That's going to be true whether the ball is at the bottom of the motion or at the top of the motion. It doesn't change. Okay? But the other force, the tension force in this case, tension is a pulling force. So it pulls this way. Okay? Unlike the previous problem, now we see that these two forces are not in the same direction. Right? So we have to account for that. First question, can these two forces be equal to each other? No, right? Why not? If they were equal to each other, what would be the net force on this ball? It'd be 0. What would it do? It'd move in a straight line, right? It would just fly off this way, right? But that's not the case. It continues in there, right? Which one has to be bigger, T or W? T, because the net force has to be pointing which way? Towards the middle, right? So, getting back to our problem over here, right? The net force in this problem is T plus W. So that looks exactly the same as the previous problem. But in this case, W is still pointing downward. But our directions, when we're talking about circular motion, aren't necessarily concerned with up and down. We're concerned about towards the middle of the circle versus away from the middle of the circle. In this case here, this weight force, still pointing downward, still the same direction as it was in this problem, but now it's pointing away from the center as opposed to towards the center. And so here we go T plus, and now because that weight force is pointing away from the center, it's going to be negative. Okay? M and V and R didn't change from the previous problem. So the right-hand side of this equation, mv squared over r, is still going to be the same as it was before. But now we're going to solve this problem, we would actually add that W force. Does that make sense? Yes, no, maybe? So this, sorry, I'm running out of room here at the bottom. Mass is 0.3, V is 4.15, and then R is 0.8. Square that velocity. Yes, no, maybe? Maybe that's, maybe we rounded something different, I don't know. So,
I got 9.401.
because you just copied it off the board?
No,
Or
it's just-
maybe we rounded differently. So,
It's close enough.
so okay. When I did mv squared over r,
I got 6.075.
yeah.
But I didn't round it before I added.
6.078.
Yeah.
Okay. And then now we have to add this.
No, I still get 9.03.
Yeah,
I got 9.401 too. Did you square for straight short?
And see, now I got 9.02. So
What did you do?
I did it exactly like that.
you know what I might have done the first time? Oh, that's what I did. I know what I did.
No, I know, but
When I did it the first time, I made the radius 0.8 instead of 0.85. So that's what it is. But this is not.
So then it is 9.02.
Yeah. Sorry.
9.02 is accurate.
Yep. Yeah. Sorry. What happened? I did it wrong. Good there. So when you're swinging this ball, right, or if you've ever done the demonstration where you have a big bucket of water and you swing it, have you ever done that before?
Yeah.
Like that, but on a bigger scale, right? Okay. That works like if you have a bucket of water, you can swing the bucket like this and it won't fall. Where does it feel the heaviest? It feels the heaviest down at the bottom, right? Your arm, when you're swinging the bucket around in the circle, your arm is the tension force, right? Look at how much bigger the tension force is when the bucket or the ball is going through the bottom of the circle than it is going through the top of the circle, right? It's 3 times as heavier down there, right? Why? Because in this case, gravity is helping centripetal force because it points towards the middle. Your arm doesn't have to do as much when the ball's up at the top because gravity's helping it out. But here, because gravity's pointing away from the circle down at the bottom, your arm not only has to balance out gravity, but it has to do the centripetal force all on its own. So it's got to do 2 things. It's got to balance gravity and provide centripetal force, and that's why we get it so big. Okay? Good there? Practical application. Here's this plane. It says an 80-kilogram stunt pilot has been diving vertically with a speed of 75 meters per second. He has to pull out of his dive while maintaining his speed, but the centripetal force must not exceed 7 Gs. That's what we call 7 times the pilot's weight here on Earth. What is the minimum radius of the circle that the pilot can take? So, this question here is asking us for a radius. Right? It tells us that the mass of this stunt pilot is 80 kilograms. It tells us that he's traveling at 75 meters per second. Okay, good there? All right, based on the previous 2 problems, well, let's go here. This plane is not quite in the spot that I wanted. I can't do that right now, but that's okay. All right. Instead of right here, let's pretend this plane is right here, at the very, very bottom. Okay? We know that in order to go in the circle, this has to be true. The net force has to be equal to the centripetal force. Yes? And so, we draw ourselves a free body diagram. When the plane is at the very, very bottom of the loop right here, just like in the previous problem, there are 2 forces acting on the pilot. One, gravity is still going to be acting on the pilot. If gravity was the only force acting on the pilot, he would fall downward with an acceleration of 9.81. But here, this plane is making a circle. And so there has to be a net force pointing towards the middle. What prevents the pilot from falling downward? Is there a tension in this case? There's not a string attached to the middle, right? What keeps him from falling downward? Well, yeah, where gravity would make him fall downward, right? Okay.
Air resistance.
What's he sitting in? A plane. The seat of the plane keeps him from falling downward, right? So that means, Robert, it's what? It's normal force, okay? There is a normal force acting on him coming from the seat. Even though I may not have drawn it to represent it accurately in this picture, what has to be true about the normal force compared to the gravitational force? If it was the same, what would he do? Go in a straight line, right? Has to be greater because there has to be a greater force towards the middle than away from the middle, right? And so here, this left-hand side of the equation looks just like this. Again, we're dealing with a combination of two forces that are combining together, hence a combination, right, to make the centripetal force. All right, good there? Okay, let's start plugging in some things that we know. What does the weight force have to be equal to? Weight is always equal to what? M times G, right? Weight is always equal to M times G. We know the mass of the pilot in this case is 80. G is always G, right? So we do 80 times 9.81. Wow. Okay, 784.8. Okay. Now, here's where we interpret this problem a little bit more. Okay. Indirectly, they have given us the normal force. And it comes with this statement right here. Okay? Are we familiar, or at least have we heard the concept of a G-force before?
Well, there's that movie.
Yes, but that was a terrible movie, so we're not going to talk about that.
There were two sound both of the driving.
Yeah.
Good.
No, not good. So, because any movie about a gerbil, not good. Or was it a guinea pig?
They were hamsters.
Hamsters. That doesn't make sense. Like that would be H force then, wouldn't it? Like wait.
They were guinea pigs.
Okay, it's like I thought they were guinea pigs. So,
Yeah,
all right. So, when we talk, a lot of times G forces get discussed when we talk about things like this. When we talk about like stunt pilots and stuff like that. Okay. We started this discussion on Monday, actually maybe on Friday, with the idea of the elevator. The elevator going up and the elevator coming down and how that makes you feel differently, right? Here, we said that your sensation, back in the elevator, your sensation of weight or what you feel like doesn't come from gravity, it comes from the normal force. If the normal force is greater than gravity, like when the elevator is moving upward or when you're on power tower getting shot in the upward direction, normal force has to be greater than gravity. And that makes you, quote unquote, feel heavier. Yes? Maybe, yeah, no, maybe, right? When we're going downward, normal force is less than gravity. When the elevator first starts going down at the top of the building, or when power tower drops you from the very, very top of the ride. In that case, weight, gravity, is greater than the normal force, and you quote unquote feel lighter or feel like you're floating. Okay? So what we feel like doesn't come from gravity, it comes from this normal force. Okay? And in this case here, it says we cannot exceed 7 Gs. As you're sitting here in your chair, what's true about your normal force versus your gravity force? It's the same. And as you sit right there in your chair, gravity and normal force are the same. Because why? Well, what are you not doing? You're not accelerating, right? Okay? You're not accelerating. You have zero acceleration. When this is the case, this is what we refer to as 1G, where your normal force is exactly equal to the gravitational force acting on you. If we want to move you upward, what has to be true about the normal force? Well, it needs to be greater, right? If we wanted to move you upward with an acceleration, here, let's see if we can piece this together, okay? If I wanted to move you upward with an acceleration equal to 9.81, how big would your normal force have to be? 2 Gs. It would have to be 2 times the gravitational force. Well done, everybody. That was good. So in this case here, what we're saying is that this pilot cannot experience a normal force greater than 7 times 784.8. Okay? Does that make sense? Because that is 7 G's. Okay? Good.
It's a random question.
Good.
Say that like you got the board.
Yep. Yeah.
You're like big enough to like this thing like board.
Sure.
And say like you jump into it, would you go on to the exact opposite side and seal reduce the center? So you could be like
Let's finish this problem, then we can talk about it. Okay. 'Cause I want to finish this because this is kind of important to the test, one part of the test. So, but then I will answer that question for you tomorrow. So, yeah. All right. So, good. All right. So now, this case, right? Does anybody do 784.8 times 7? 5,493.6. Okay, so that goes there, plus 784. But which way is that 784.8 going?
Down.
Down, right? So, that's down. But is that important in this problem? No. What is important about the direction of that weight force in this problem? What path are we following here? A circle. So what's positive and what's negative when we talk about the circle? Towards the center is positive, away from the center is negative. Which way does this gravitational weight force point? Away from the center. So in this case here, this is going to be negative 784.8. Okay? What's always, always, always true about centripetal force? mv squared over r, right? So m is 80, v is 75, and what did this problem ask us for? R. Do this first.
Did you round that?
Yeah, it's like 95.56. So do this first, right?
Alright, that is what it's 5, 4, 9, 7, 6, 7, 8, 4, 7, 8.
Okay. Then, like algebra-wise, you would multiply both sides by r.
Alright, do that.
Okay. Then do this, then divide by the
Oh, I
answer.
didn't divide, that's okay.
Yeah. So divide, because now you multiplied by
I'll
r.
steer like a
5,
bird.
6,
How many there's a bird?
I don't. Keep an eye on it.
So is the test just like questions like these? Is it all calculations?
No, there's multiple choice questions.
About like the circular.
Yeah.
Is there going to be stuff about the like the tangential speed?
Yes, about tangential speed, rotational speed, those kind of things.
no, mine were all super.
All right. We good here? We don't have enough time to do this whole problem, but let's go back. Let's look at number 3. Okay. So here's the Ferris wheel, or here's the Ferris wheel. Okay. in the Ferris wheel, you're going in a circle. Okay? Always, 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 there's going to be this, right? There's going to be a gravitational force pulling on you. Okay? Up at the top, that gravitational force is pointing towards the middle of the circle. And that means it's helping with centripetal force. But down at the bottom, the gravitational force is away from the middle of the circle, so it's not helping. It's actually hurting centripetal force, right? It's making something else be bigger than gravity itself. Okay? Here, normal force is providing that other force, working in combination with the gravitational force. Here, tension is working in combination with that gravitational force, right? Sometimes they work together, sometimes they have to work against each other. Sometimes they have to work against each other, okay? That's what this problem was about. So, in this problem, what's providing the other force here? What's the other force that's acting on the people on the Ferris wheel? It's normal force, again, okay? So, normal force, in this case, would have to be greater than the gravitational force, just like the airplane problem that we just did. Yes, no, maybe? That's okay there? Okay. But this one is a little bit different up at the top. If we're talking about an airplane, if the airplane got up to here, gravity would still be going this way, but now, when he's upside down, the seat is on top of the pilot. Yes, no, maybe? It's still pushing down, right? So those two work together. But on the Ferris wheel, the seat is never on top of the rider. So the normal force would always be going in the upward direction. The net force in every situation has to point towards the middle. That has to be true to make something go in a circle. We've analyzed the bottom of this situation already. When something is traveling through the bottom, normal force has to be bigger than the gravitational force or the weight force because we have to have a net force towards the middle. Yep. As long as there is some combination of forces that point towards the middle, we'll go in a circle. Okay? Right. Can the value of W change, though? It's always equal to M times G, so what has to change? What does it feel like when you go over the top of the Ferris wheel? Not quite, but you feel like lighter. Okay? What if we went the right speed? What if we no? What if we went the right speed with the right radius? Because the centripetal force has to be equal to mv squared over r, right? So in this case, hold on. Do this. All right, so here. We've established that this has to be true in all points of this circle. Okay? At the bottom, because the weight is pointing away from the circle, normal force has to be greater. What do you feel like as you go through the bottom of the Ferris wheel? You feel a little heavier. Now, on the Ferris wheel, because V isn't very big, you don't need a whole lot more normal force than you do gravity force. But at the bottom of a roller coaster, when V is much bigger, we need more centripetal force, so normal force has to be a lot bigger than gravity. When do you experience that sensation on the roller coaster? No. When you're going down through the bottom. Think about what you feel like at the bottom of that first hill, like you're kind of getting like pushed down into your seat, right? Yeah. But up at the top, right, normal force is less than gravity. When do you experience that on the roller coaster? At the top of hills, right? Those last 3 hills on the Magnum, those little like, whoosh, whoosh, you feel like you're almost like flying out of your seat? Yes? Why? Because the normal force is less than gravity. You have that feeling of being less than what you weigh. Maddie, now, if we have the right combination of mass, velocity, and radius, that m times g exactly equals this, do we need any normal force at all? If m times g is the right combination to match this side of the equation, normal force doesn't play any role. What does that feel like? How much lighter? If normal force is 0, how many g's is that? 0 g's. Does that make sense? When normal force is 0, that's 0g. That's the video we were watching yesterday, right? As, here, right? Okay, so there's my airplane, right? If you're inside, gravity's pulling you down. Gravity also pulls the plane down, right? What's true about the rate at which gravity and the plane and you fall? Same rate. Is there any floor underneath you here? No. So you have no what? You have no normal force. Not no weight. You have no normal force. And if you have no normal force, what do we feel like? You feel weightless, right? So we can make this Ferris wheel or roller coaster go the right speed. That gravity is the only thing we need, and then we get that weightless sensation. Okay. You say again? 1 revolution in 12 seconds. You can calculate 2 pi r. Yeah. So.
Is our test just a test? There's nothing special to it?
Yeah, I mean, just fun.